Alright guys, so welcome back, and we're just going to have a very quick flyby of transcription. So transcription is the process of getting DNA to RNA, so it's this arrow here, transcription, okie dokie. So transcription has three processes. It has initiation, extension and termination. Now initiation occurs when the RNA polymerase finds the promoter. So obviously RNA polymerase scans along the DNA finding until it finds the special sequence called the promoter, which tells the RNA polymerase now this is where to bind. So we'll pretend that this is our promoter sequence here and that the RNA polymerase goes ahead and binds. Okay, so that is simply initiation. Now extension is when the DNA double helix unwinds and the RNA polymerase reads the template strand and adds nucleus to the growing end of the strand, which is the 3' end. So the RNA polymerase works its way down, as it does, ticking away, complementary base pairing, and adding to the mRNA strand. So we'll draw it just going down, and it does eventually work all the way to the bottom until it hits the terminator. So RNA polymerase will then hit a terminator sequence, and then it stops transcribing, and it says, right, that's it, the mRNA molecule is now ready. So how does it know which strand to read? Because obviously it's got two strands here. So how does the RNA polymerase actually know which strand to read? Now, what it wants, and do you remember when I said in the previous video that RNA runs from the 5' to the 3' direction? So what the RNA polymerase actually wants is a copy of the DNA that runs from the 5' to the 3' end. But to do that, what it needs to do is it needs to copy from the 3' to the 5' end to get a copy of that 5 to 3' end. So what you'll see is that the mRNA here is actually complementary to the 5 to 3' end here, so it's exactly the same. Now, if it wanted a copy of the 3 to the 5' end, which it doesn't, but if it did, then it would have to use this one as your template strand, and that is what we call this strand. We call this one, so the 3 to the 5 is the template strand. The 5 to the 3 is your coding strand, because that's the code that the RNA polymerase actually wants. Okay, so this is your mRNA molecule, so mRNA that the RNA polymerase makes. Now mRNA stands for messenger, RNA, and it's going to go off and it's going to find a nice ribosome to translate it. If you're a prokaryote, that is. Now, if you're a eukaryote, like we are, the phrase not so fast comes in. So, this is where we leave the prokaryotes because they've got an easy life. And I've also done a picture here, guys, that I've got off the internet for you, in case that makes any more sense than my crude drawing up top. Now, because eukaryotes like to be complicated, we have a little bit more processing to do. So the molecule up here, if you're a eukaryote, would actually be called pre-mRNA, if you are a eukaryote. Okay? Now we've got stuff to do as a eukaryote, because obviously our genes are separated by introns and exons. So our DNA is separated here. So this is the gene here, DNA is separated by introns and exons. Now we don't want the introns because they don't code for anything useful in this case. So what we're going to have to do is remove all of the introns and splice together all of the exons. But before we do that, we need to add a little bit of protection. And this comes in the form of a 5' cap. Now I'll be going into why we need that in a little bit, but that's what happens first. The 5' cap is added. Then we excise all of the introns and we splice the exons, so goodbye introns, and shunt together for all the exons. And then we undergo polyadenylation. Now this is just a process where on the very end we add a load of A's. So poly meaning many, adenylation, A. Loads and loads of A's. And then it's off to the cytosol for translation by the ribosomes. Now, that is pretty much what happens, but obviously something else that we can do that's real cool as eukaryotes is we can do alternative splicing. So this section of DNA here, and these are obviously introns, we have 5 exons. Now they're the coding bits, the bits we're interested in. Now if we splice together exon 1 to 5, we get protein A. If we splice together exon 1, 2, 4 and 5, we get protein B. So you see we skipped out 3. 3 is no longer there, we get a different protein. You see something's missing? And if we string together 1, 2, 3, and 5, so once again we're missing another one, we're missing 4 from this one, we get protein C. So I just thought that would be something cool to show you, that one length of DNA can in fact code for, you know, a couple of proteins rather than just the one. But I'll leave it there. So for eukaryotes, it's off we go, and we're off for translation, and we can pretty much leave it there. But why do we add a 5' cap and a poly A tail? And this is simply protection for the journey. Now, I'm just going to draw a very quick and crude table up here to try and show you why we need protection for the journey, because we are eukaryotes. Okay, so let's say transcription, translation. I'm just shorthanding it, so you've got transcription and translation here. And you've got pro, and you've got eu. Obviously, prokaryote, eukaryote. Now for both, for prokaryote, transcription and translation happens in the same place, and that's the cytoplasm, because they have no nucleus. So this process is coupled. As you have transcription going along, so you've got your transcription kind of ticking along, you've got building your mRNA molecule, you can also have translation happening at pretty much the same time. So it really doesn't have to travel very far at all. So there is no need for this protection on a prokaryote at all, because it's probably not travelling anywhere. And then you've got the eukaryote, where our transcription happens in our nucleus, and our translation happens in the cytoplasm. So the eukaryotes need protection for the journey, so this is where we get our 5' cap and our poly A tail. And one thing that I haven't mentioned until now is the UTRs. Now UTR stands for untranslated sequence. And that it literally is like it says on the tin, it's untranslated sequence. It does not get translated. The bit we're interested in, the coding sequence, the CDS, this is what eventually becomes the protein when it undergoes translation. Okay? So essentially we add a 5' cap and a poly A tail to eukaryotes because they've got a bit of a journey to make, whereas prokaryotes don't have that journey to make, so there is no need for that protection. And then once we have our mRNA molecule, it kind of goes off through the nuclear pore. This is a nuclear pore, which I thought was real cool. And it's going to go off and find a nice ribosome and get itself translated. Alright, so I'll leave it there, guys, and I'll see you in the translation video.